Hi, so I would discuss the hypothesis tests with example. So yeah, just one by one. So at first, the test by deviance, and we would do the goodness of fit test first. We will do. And the GLM1, so this is this model. So the number of, basically the proportion of dead is response and the concentration is predictor. Then estimates are here. Then we would like to see this, if this model is enough to explain the variability in proportion of dead. Then we can calculate the deviance and yeah, so deviance and the degrees of freedom. So we have the two parameters. And remember that this data set have 5 observations. So n is 5 and p is equal to 2. So n minus p is equal to 3. Yeah, n minus p is equal to 3, and the residual deviance. So deviance is 0.37. So the upper tail probability is equal to 0.944. So it's pretty large. So that means this model explains the sample proportion of dead pretty well. So model is not rejected. So GLM1 is sufficient to explain data. So next one, the tests by deviance for smaller model, omega, and larger model, capital omega. So we have one model, GLM1. So we prepare another model that has 2 predictors. One is the concentration, and the other is the square of concentration. We have to put I to make it work. So I don't have any logical reason, but we have to put I if we put the square of concrete as predictor, or any variable in the GLM function or LM function. Then we fit the model, and the deviance of this model is 0.19, and the degrees of freedom is 2, because this model has 3 parameters. So intercept and concrete and the square of concrete. So p is equal to 3, so n minus p is equal to 2. So what's the test to compare omega and omega, the capital omega? Then we take the difference between deviance. Okay, so this is the deviance for smaller model and the deviance for larger model. And the degrees of freedom is the degrees of freedom for larger model minus degrees of freedom of smaller model. So this is the 3 minus 2. So, oh, sorry, the other way around. So df omega, so this is 3 minus 2, so this is 1. And the p-value is 0.668, so that is much larger than 0.05. So we do not reject null hypothesis. So our model, the smaller model is, I would say the larger model isn't significantly better than the smaller model. Actually, the smaller model is even sufficient compared to the saturated model. So it's almost the expected result. Yeah, and the same result can be obtained by this ANOVA function. So it reports both this deviance and both degrees of freedom, and also the test results. So the same results. So anyway, so the smaller model is good enough. Larger model isn't significantly better. And this can be used naturally to test coefficients, because the second model and the first model, the difference is whether or not beta 2 is equal to 0. So GLM1, we don't have the quadratic term, and the GLM2, that we have quadratic term. So we can use this test for the test for beta 2. But beta 2 can be tested directly, so walled test. So if we see the summary of the GLM2, we can see the estimate as well as the standard error of estimate, the Z value and the P value. And actually this P value corresponds to the test, walled test. So walled test is basically the beta hat divided by standard error of beta hat. So this value is approximately normal 0.1. So you can get the P value with this property. So still we have almost almost the same P value, and the null hypothesis is not rejected. So smaller model is as good. That means the beta J is not significantly different from 0. And lastly, that we discuss chi-square tests for goodness of fit. So this isn't included in the textbook, but we have studied the theory. So just one example. So this is basically the comparing observation and the fitted value. So at first we think about observation. So this is the sample proportion, basically the data for sample proportion. And the sample proportion is the dead divided by 30. So remember that the sample size is 30 for all lines. So first one, about 7%, 27%, 50, 77, and 90%. Okay, and the residual. So we have already fitted model. So actual minus fitted, that is residual. So residual is just negative 2.3%, positive 2.8%, 0, positive 0.5%, negative 1%, 1.1%. Then now we have to calculate the variance of this quantity. And the variance of y is basically the mu times 1 minus mu divided by n. So this is the fitted value times 1 minus fitted value over 30. So this depends on the observation. So this is, the 5-dimensional vector. So here 30 is because all lines have the sample size of 30. So otherwise we have to use the different number for each line. Then chi-square value is the sum of the squared residual divided by v. So this is component-wise the division. So for we have the residual square over v for each observation, then take summation later. Then chi-square statistic is 0.36, and if we calculate the p-value, we have degrees of freedom 3 because we have 5 lines and we have the 2 parameters. And actually this is 0.946. I think previously that was 0.944, so slightly different, but the conclusion is the same, and the GLM1 is not rejected. So GLM1 is sufficient to explain the data.